We will begin our discussion on the periodic trends. I have said this in the previous video that we are going to learn about periodic trends in near future, and this is the beginning of periodic trends. We will begin with atomic radius. The first periodic trend that we are going to learn here is atomic radius. Atomic radius means the distance from the center of nucleus to the outermost shell containing electrons. If I derive it, there is an atom containing 4 electrons like this, and here is a nucleus. From the center of the nucleus to the outermost shell containing electrons, this distance is known as atomic radius. But quantum mechanics is something like a teaching. Quantum mechanics teaches us that an isolated atom cannot have a definite size. That means we cannot actually define the size of an isolated atom. Hydrogen, when taken alone, it is an isolated atom. Lithium, when taken alone, it is an isolated atom. Helium, when taken alone, it is an isolated atom. Likewise, one single atom cannot have a definite size. So, we define the atomic radius when the atoms are in combined state. To give the atomic radius of an atom, we should consider their combined state. That means when they are engaging in a bond. Always there should be a bond in the atom to define its atomic radius, right? So there are 3 types of atomic radius. 3 types of atomic radius are covalent radius, metallic radius, and van der Waals radius. First of all, we will discuss about covalent radius. Covalent radius means when the atoms are bonded by a single covalent bond, the distance between two nucleus is taken as the internuclear distance, and then it is divided by 2 to take the covalent radius. For example, like this: hydrogen. 2 hydrogen atoms form H2, right? Then hydrogen atoms are bonded together by a covalent bond, a single covalent bond. Here there is a 2 nucleus, and this distance between 2 nucleus is known as internuclear distance. This distance is d, and this distance divided by 2 gives the value of covalent radius, right? 1/2 of the distance between 2 nuclei of 2 like atoms bonded together by a single covalent bond is known as covalent radius. Keep in mind that HCl, hydrogen and chlorine also can form a covalent bond. But we do not take such situations to measure the covalent radius. 2 like atoms should join together by a covalent bond in order to take the covalent radius. Like H2, N2, O2, like 2 like atoms should join together by a covalent bond to measure the covalent radius. So because there is only single covalent bond between these 2 like atoms, it is also known as single bond covalent radius, right? Atomic distance is another name for internuclear distance. So when the values are taken in picometers, there is an equation to find the distance between 2 nucleus of 2 atoms, right? If we take this atom as A atom and this atom as B atom, here the atomic radius of A atom plus atomic radius of B atom plus 9 times the difference of electronegativity of A and B according to the Pauli scale gives us the interatomic distance between A and B. Right? There was a past paper question on this equation, so you should remember this one also. This equation was derived by Skomaker and Stevenson. Then the next type of radius is van der Waals radius. Van der Waals radius means 1/2 of the distance between 2 equivalent non-bonded atoms in their most stable arrangement. So we will take examples as HCl, right? HCl. Here hydrogen atom is there, here chlorine atom is there, here hydrogen atom, here chlorine. The distance is taken in between two like atoms. Chlorine, chlorine, they are like atoms. But they are bonded to a different atom. Chlorine is stable when it is filled with another electron. That electron is given by hydrogen. So here chlorine is in its most stable arrangement. Most stable arrangement. Right? So two like atoms, the distance between two like atoms is taken in their most stable arrangement. But these two like atoms are not bonded to each other. They are in their stable arrangement. But these two atoms are not bonded to each other. So this is known as non-bonding radius. So අපි එකම ඇටම් එකක මේ විදියට වැන්ඩවාල්ස් රේඩියස් එක මෙට්ලික් රේඩියස් එක එතකොට කෝවේලන් රේඩියස් එක තුනම ගත්තොත් එහෙම වැඩිම ඩිස්ටන්ස් එකක් වැඩිම රේඩියස් එකක් එන්නේ වැන්ඩවාල්ස් රේඩියස් එකේ because it is non-bonding radius. No overlappings are there between the two atoms, so the highest distance is in van der Waals radius. The third type is metallic radius. I am going to draw a metal like this, right? You will see that here atoms are arranged tightly packing together like this. I am going to zoom out these two like this. Metallic radius means the one half of the distance between two nuclei of two adjacent metal atoms in a metallic structure. In a metal like this, atoms are tightly packed like this, right? These are two adjacent atoms. If we take out these two adjacent atoms and measure the distance between two nucleus of these two atoms and take the half value of that, then that is metallic radius. You should remember a point like this. Metallic radius is equal to cation radius. We will learn what cation radius in near future. Till then remember that metallic radius is equal to cation radius. Terming atomic radius, we generally refer to covalent radius. So from now we will discuss about covalent radius. Covalent radius depends on three factors. First one is number of energy levels in an atom, then effective nuclear charge, screening effect or shielding effect. Number of energy levels in an atom is an obvious fact. You know that when the number of energy levels in an atom increases, the atomic radius also increases. It is very obvious thing, right? We will compare hydrogen and lithium, right? Hydrogen have just one energy level and lithium has two energy levels. We will take it in same size here like this. First energy level and the second energy level. Here hydrogen, this distance from the nucleus is covalent, and here the distance has increased when the number of energy levels increased. So that is very obvious. When the number of energy levels of an atom increases, the atomic radius increases. Next factor is effective nuclear charge. Effective nuclear charge is the actual charge felt by electrons in an atom, right? We symbolize it by ZeFF. There is an equation to find the effective nuclear charge. When the atomic number of an atom is reduced by the number of co-electrons, we can find the effective nuclear charge. We will take lithium for an example. I am going to draw lithium. Here two electrons, here is a nucleus, and here one electron. So atomic number is 3. Number of co-electrons means number of electrons in the inner energy level. Here this is the inner energy level. There are 2 electrons. I am going to subtract it. So the effective nuclear charge of lithium is 1. Another example. I am going to take sodium. there are 3 energy levels like this. 2 electrons in the first one, 8 electrons in the next one, and 1 electron in the last energy level. Here sodium. Atomic number is 11. Co-electrons, how many? 10 co-electrons. There are 2 inner energy levels, so 10 electrons. Effective nuclear charge is 1. Another example, I'm going to take beryllium. 4. 1, 2, 3, 4. Here is a nucleus. Here's beryllium. Atomic number 4, co-electrons 2. So ZDFF is equal to 2. Likewise, effective nuclear charge can be calculated. When the effective nuclear charge increases, the attraction of the nucleus toward the outermost electrons increase, so that the atomic radius decrease. I'm going to explain it for you now. So we know that in here, lithium, I'm going to draw lithium and beryllium here. I'm going to compare those two like this. Here is the nucleus of 2 electrons and 1, 2 electrons and 2 electrons in the outermost shell. Like this. Right? In lithium, here is a nucleus. We know that effective nuclear charge is 1. In beryllium, effective nuclear charge was 2. That means, මොකක්ද අපි කිව්වේ effective nuclear charge කියලා කියන්නේ? The actual charge felt by electrons. Actual charge felt by electrons is 1. 1 කියලා charge එකකින් මේ outermost electron එක nucleus එක පැත්තට ඇදගෙන ඉන්නවා. මෙයා 2 කියලා charge එකකින් nucleus එක පැත්තට outermost electrons ටික attract කරගෙන ඉන්නවා. So when we compare these two, 1 is lesser than 2. More attraction force is exerted on the outermost electrons of beryllium from its nucleus than lithium. I think you understand my point. Effective nuclear charge is 1 in lithium. So 1 කියලා force එකක් දීලා outermost electrons ටික attract කරන් ඉන්නවා lithium වල nucleus එකේ. In beryllium effective nuclear charge is 2. 2 කියලා force එකක් දීලා outermost electrons ටික attract කරන් ඉන්නවා එයාගේ nucleus එක. So that වැඩියම attract කරන් ඉන්නේ කවුද මෙතෙන්දී? Beryllium. Obvious fact is that beryllium attracts more. එතකොට when we compare lithium and beryllium, there are 2 energy levels. දෙකේම 2 energy levels තියෙන්නේ. But beryllium ගේ outermost shell එක attract වෙලා තියෙනවා වැඩියෙන් nucleus එකට than lithium. So lithium's atomic radius is higher than beryllium. The next factor that we should discuss is screening effect. It is also known as shielding effect. We know that even though there is an attraction by the nucleus to the outermost electrons, electron-electron repulsion is there. Electrons repel each other, right? There is an attraction from the nucleus to the outermost electrons. But electrons repel each other. This, like this. එතකොට අර nucleus එකෙන් outermost shell එකට තියෙන attraction එක shield වෙනවා. shield වෙනවා කියන්නේ අපි කියන ආවරණය වෙනවා, cover වෙනවා වගේ වෙනවා. මේ electron repulsion එක හින්දා. මේගොල්ලන් repel කරන නිසා මේ attraction එක පොඩ්ඩක් shield වෙනවා. අඩු වෙනවා. එතකොට මේ විදියට screening effect එක වැඩි වෙද්දී ඔයාලට පේනවා මේකෙන් මේක වැඩියෙන් repel කරද්දී තව ටිකක් මේ outermost එක ඈත් වෙනවා. attraction එක අඩු වෙනවනේ. එතකොට nucleus එකෙන් තියෙන distance එක වැඩි වෙනවා. එතකොට inner shells ගාන වැඩි වෙද්දී screening effect එක වැඩි. දැන් මෙහෙම හිතන්නකෝ. එතකොට මෙතෙන්දී මේක මේ දෙකේ repulsion එකක් තියෙනවා. ඔය විදිහට. ආයෙම මේ දෙකේ repulsion එකකුත් තියෙනවා. එතකොට මේ දෙකේ repulsion එකකුත් හැදෙනවා. එතකොට repulsion force එක වැඩි. screening effect එක වැඩි. When the number of co-electrons increase, screening effect also increase. Because of that, nuclear attractions become less. So we can say that When the screening effect increases, atomic radius increases. Screening effect එක වැඩි වෙනවා කියලා කියන්නේ electron repulsion එක වැඩි. Because of that, nuclear attractions become lesser. When the nuclear attractions become lesser, electrons can spread in a larger particle area. Because of that, atomic radius increases. Now we are going to summarize the facts that we learned up to now. Atomic radius variation down groups. Right, we know that when going down the group, number of energy levels in an atom increases. Very obvious fact, when the number of energy levels increase, atomic radius increases. Another factor is there to compare down the group. That is, when going down the group, number of co-electrons increase. Hydrogen has no co-electron. Lithium has 2 co-electrons. Sodium has 10 co-electrons. Likewise, when going down the group, number of co-electrons increase. Because of that, screening effect increases down the group. Because of the increasement in the screening effect, atomic radius increases. We can say, when the screening effect increases, nuclear attractions become decreased, then the atomic radius increases down the group. So the first atomic trend here is, when going down the group, atomic radius increases. Then we will compare the atomic radius variation across the period. Effective nuclear charge increases across the period. We will get some examples to calculate here. Lithium, beryllium, boron. Lithium atomic number 3, number of co-electrons 2. Here 1 is equal to ZeEF. In beryllium atomic number 4, co-electrons 2. Effective nuclear charge is not 4, it is 2. Effective nuclear charge 2. In boron atomic number 5, co-electron number 2, effective nuclear charge is equal to 3. Likewise, we notice that when going across the period from left to right, effective nuclear charge increases. Effective nuclear charge increasement means nuclear attractions become increased. Because of that, atomic radius decreases. When the nuclear attractions become higher, atomic radius becomes low. So the next periodic trend we are going to learn here is, atomic radius decreases from left to right in a period. We discussed that atomic radius increases down the group and atomic radius decreases from left to right in a period. Here in this chart, it has marked from right to left, right? We discussed from left to right and it has marked in this way. We discussed in this direction. So even though we discussed so, you better see here there are little variations in values. Nitrogen and neon has the same value. It cannot happen. There should be a decreasement, but there are same values. And here an increasement. It is also a variation. And there are like little fluctuations in the values. It is better if you could remember the values to get highest marks in the examination, right? So study this value table and remember those fluctuations carefully. Thank you for being with me till the end. I think this was helpful to you. If so, don't forget to like and subscribe to my channel.